I want to echo Mr. Sumner's thanks to that group of students who took the PSAT and stopped by and spent even more time with us to answer questions for you, especially those that may be really considering a Louisiana school experience. They had been with us 4 hours taking that test, so I know they're exhausted, but they still gave it their all, and I think you'll benefit from that experience. For our next, we're going to welcome some of our teachers, and first we're going to introduce Mr. Randy Key, a professor of mathematics who's going to give you an interesting explanation about the number 1, and then he's going to let you see a portion of one of his Precalculus mathematics classes that was filmed earlier. So, Mr. Key.
Hey Future Eagles, I'm Randy Key. I'm a math professor here at the Louisiana School. I teach Introduction to Engineering, Algebra, Trig, and I teach the Multivariable Calculus class. And as a mathematician, one of the things that we often say is that 1 plus 1 equals 3 for extremely large values of 1. So in honor of that, what I want to do for you now is to prove that 1 equals 2, and I will do that based on some introductory algebra, but I need to review a tiny bit of it, multiplication. So this says x plus 2 times x minus 2. And in my algebra class, I learned to multiply these guys that I want to use the FOIL technique. So I'll say x times x is x squared. X times negative 2 is negative 2x. 2 times x is 2x. And 2 times negative 2 is minus 4. But when we combine like terms, these guys cancel, and I'm left with x squared minus 4. So what I want to know is, can I go more quickly from this to this? So if I try a similar example and instead look at maybe x plus 3 times x minus 3, I wonder, does that equal x squared minus 9? And to confirm that it does, we can just do the multiplication again. X times x is x squared. X times minus 3 is minus 3x. 3 times x is 3x. And then 3 times negative 3 is minus 9. Notice again, these terms cancel, so I get x squared minus 9. So this has a special name. What I actually want to do is not go from here to here, but the other order. I want to go from here and rewrite it as a product. So if I had x squared minus 25, I might recognize that it looks very much like this one or this one. So I would hope that this is x plus 5 times x minus 5. If you want to double check my math, you'll see again the x times x is x squared, the 5 times negative 5 is the minus 25, and the other two terms are going to cancel. This thing has a name that's called a difference of squares. It doesn't have to be x squared and 25, it could be literally anything that's squared in the first and the second position. This one would be x plus y times x minus y. And the one that I think we'll see this time is if we have a squared minus b squared, we'll be able to write that as a plus b times a minus b. So this is just an algebra review. What does it have to do with proving that 1 equals 2? Well, let's see. To prove 1 equals 2, what I want to do now is use an algebra approach. So I'm going to choose a couple variables to do some work for me. So I'm going to let the variable b equal the variable a. And now I'm just going to apply some algebra. Anything I do to one side, I'll have to do to the other side. The first thing I want to do is multiply both sides by a, and when I do that, I'll get ab on the left is equal to a times a, that's a squared. The next thing I'll do is subtract the number from both sides, but I'm not sure what that number will be. So I'm going to subtract b squared from both sides of the equation. So I'll have ab minus b squared on the left, and a squared minus b squared on the right. So what I recognize is a squared minus b squared. This is why we reviewed this over here. I just learned that a squared minus b squared is equal to this special product. This is factoring the right-hand side. So the right-hand side has to be a plus b times a minus b. The left-hand side, to factor it, I just look for a common factor. So this is undoing the distributive property. I have a b here and here. So if I factor a b out, I'd be left with a minus b. And if you double check that, when you distribute, b times a is ab, b times negative b is negative b squared. So then when I take a look at this, I see that there's a factor of a minus b on the left. There's a factor of a minus b on the right. So at this stage, I would divide both sides by a minus b. So if this guy times him is equal to this guy times him, then these guys have to be the same. So b is equal to a plus b. And now we just refer back to the assumption we made to begin with, b is equal to a. So that means everywhere I have a b, I can put an a, or if you like, everywhere I have an a, I can put a b. So we get b is equal to b plus b, or b is equal to 2b. If I choose to divide both sides by b, I can do that. Or since this is true for any values a and b, I can just let b equal 1. If b equals 1, we have 1 equals 2 times 1, or 1 equals 2. At Louisiana School, anything is possible.
Hey guys, I'm going to shoot a quick video here for you. This is based on the review session that we did on Zoom a little bit ago. You asked that we do it on the patio, on the chalkboard. I looked over those review problems that I sent you in terms of the rational function. I've chosen 3 of those to work for you as quickly as I can. They are, I think, problems 3, 6, and 7. But I'm going to work them in reverse order. They all have a little bit of nuance going on. So if you can fast forward, if you're happy with problem number 7, you want to fast forward to 6 or 3, we can do that. So I've got problem number 7 here, y equals x minus 1 over x times x minus 3, and I need to find those things indicated on the review. I may step off screen so you can see some of the work. The zeros of this function are the values for x that make the top 0. The only thing that makes the top 0 here is x equal 1. Its multiplicity is the number of times that factor appears. X minus 1 is up there once, so it has a multiplicity of 1. Next, I need the vertical asymptotes. The vertical asymptotes occur at the values for x when the denominator is made 0. So we have x times x minus 3. So my vertical asymptotes will be at x equals 0, because x equals 0 would make this guy 0. X equals 3. Each of these factors in the denominator appears only once, so their multiplicities are each one. The next thing we need is the end behavior. The end behavior for a rational function can do one of 3 things. It can level off at some horizontal asymptote. It can go up, or it can go down. Now we know about going up and going down. We're used to that from polynomial functions. These are a little bit different in terms of finding that. So what I look at is the degree of the numerator and the denominator. And I'm going to work 3 problems, and each one has a different case. The degree upstairs of this guy is 1, it's linear. Downstairs, if I multiply that together, the degree downstairs is 2. If the degree of the denominator is greater than the degree of the numerator, then you have a horizontal asymptote at y equals 0. So that's my end behavior. So this thing has a horizontal asymptote. At y equals 0. Now, if I'm following directions, the next thing it says is to find the y-intercept. I usually save that for last. This guy doesn't have a y-intercept, and I know that because we have a vertical asymptote at x equals 0. How do you find a y-intercept? You plug in x equals 0. If I plug x equals 0 into this, I get undefined, which means this function doesn't have a y-intercept. So even though I would normally save it for the end, this one doesn't have one anyway. I think I'm ready to try to graph this thing. Things that are important to me are 1, 0, and 3. So I want to make sure I have 1, 0, and 3 laid out here. So I can say that this is 1. So this is 3, 1, and 0. Now what's going on? The zeros occur at x equal 1. That's a point that hits the x-axis. Another 0 is at x equal 3. That's a point that hits the x-axis. But oops, I did that wrong. The zeros are x equal 1. The vertical asymptotes are at x equal 3. So a vertical asymptote is not a point my graph hits. It's an imaginary vertical line that my function can't intersect. It'll approach it either going upwards or downwards. So at x equal 3, I'm going to dash this line. So when I graph this, I know that I will approach either going upwards or downwards on either side. I also have an asymptote at x equals 0. It's hard to dash the y-intercept, but I'm going to do it anyway. Just so when I graph, I remember, hey, I have a vertical asymptote there. The next thing I need is the end behavior. The end behavior is a horizontal asymptote at y equals 0. Y equals 0 is the x-axis. So I'm going to dash my x-axis out here at the end. So I know when my graph gets very, very large, I'm sure when my x values get very, very large, they won't go up, they won't go down, they will level off and approach this line asymptotically, either from above or from below. Normally, it doesn't matter if it approaches from above or below if I have a horizontal asymptote, but because this asymptote is the x-axis, what I've discovered here is I'm not exactly sure where to begin my graph. Usually I would start at in behavior, but I can't do that in this case. So this is the rare case where I need another point. It doesn't matter which point, I need to choose a value for x that isn't 1, 0, or 3. So I ask you, what's your favorite number? You can choose anything you want. I'm going to choose a large number, something bigger than 3, so I can identify the in behavior. What's your favorite number bigger than 3? 100. Why am I choosing 100? Because I don't care what the y value is. I just care if it's positive or negative. So go with me on this. 100 minus 1 is 99. That's positive. 100 is positive. 100 minus 3 is 97. That's positive. So I end up with a positive number over a positive number times a positive number. Positive times positive is positive, positive divided by positive. So what have I learned? That when x is very large, the y value is positive. That's all I need to know. I'm ready to graph this thing. I'm going to graph it from right to left. When x is very large, my y value is positive, but it doesn't go up. It must approach this as an asymptote. So I know now it approaches from above. And now I'm just going to follow my nose. I'm going to graph this going this way. I'm looking for zeros, and I'm looking for vertical asymptotes. The first thing I encounter is a vertical asymptote. I only have two choices. I can approach it going upwards or downwards. I'll run through both options each time. I can do this. I cannot turn and go down. The only way I can do that is by crossing the x-axis, and I don't have any zeros, so I have to approach going upward. The next thing I'll use is the multiplicity. At x equal 3, the multiplicity was 1. Because the multiplicity is 1, that's an odd number, so remember that means my signs change. At x equal 3 on the right, my y value is positive. So on the left, I need to change y values, so my y value will be negative. That tells me I'm going down along this vertical asymptote on the left. Still following my nose, looking for the next thing. The next thing I encounter is a 0. So I need to go intersect at this 0. Remember, if the multiplicity is odd, I will change y value. If the multiplicity is even, I will touch it and keep the same y value. X equal 1 is my 0. Its multiplicity is 1. That's an odd number. So what does that look like? I get to cross my x-axis there. The next thing I encounter is a vertical asymptote. Remember, I have two choices. I can go up or I can go down. Cannot turn and go down because I don't cross the x-axis. So I have to go up and approach that as an asymptote. Immediately to the right, my y value is positive. So immediately to the left, I'll either keep the same y value or I will change y value. X equals 0, multiplicity 1, that's odd, so I'm changing y values again. Approach going upwards on the right, I better be going downwards on the left. And now I'm going this way, I'm still looking for zeros. Oh, I don't see any zeros. I'm still looking for vertical asymptotes. I don't see any more vertical asymptotes. If I don't have zeros or vertical asymptotes, I must be at the end. That's why I use the language, the end behavior. What happens at the end? A horizontal asymptote at y equals 0. So I need to approach the line y equals 0. That's the x-axis. This is the graph of y equal x minus 1 over x times x minus 3. I will point out a couple things here for you. One is, even though this has a horizontal asymptote at y equals 0, it also crosses that horizontal asymptote. Functions may cross their horizontal asymptotes. They may not cross a vertical asymptote. Now, why is that? Because horizontal asymptotes aren't what you can't do. Horizontal asymptotes are your end behavior. All they tell me is what happens out here and out here. And if in the middle, I cross over it, that's good. So this is a pretty good graph. I'll pause this, and then we'll start right back up with exercise 6. And we're back. Here's exercise 6, which reads negative 2x squared plus 5x plus 3 over x squared plus 2x plus 1, and we want to graph this rational function. We need to figure out the same things we did before. It looks like we need to find the zeros, the vertical asymptotes, and the end behavior. Notice these are in expanded form. Well, this is something we've been practicing with polynomials. I'm going to treat these independently. But what I do with just this polynomial, maybe I need to use the rational root theorem or Descartes' rule of signs. But each of these is quadratic, and they both factor. So I factored them a moment ago, and now I'll just show you what that factorization looks like. But if you want to pause the video and double check that you can factor each of these, go ahead. So here's the factored form for this rational function y. And now that it's factored, I think I'll be able to find each of these easier. The zeros are the values, remember, that make the upstairs, the numerator 0. 2x plus 1 is the factor. The 0 is x equal negative 1/2. X minus 3 is the factor, so the 0 is x equal 3. The multiplicity for each of those is 1. The vertical asymptotes occur when the denominator is 0. X plus 1 is the factor, so that vertical asymptote is x equal negative 1, and its multiplicity is 2. Remember, I said the end behavior was all about the degree of the numerator or the denominator. In exercise 7, the degree of the denominator was bigger, so we had a horizontal asymptote at y equals 0. Let's look at this one. I'm going to look back at this form, and I'm not even interested in all of this stuff. I'm only interested in this guy and this guy. The degree upstairs is 2. The degree downstairs is 2. If the degree upstairs and the degree downstairs are the same, you have a horizontal asymptote at y equal the quotient of the leading coefficient. So I have a horizontal asymptote at y equal, well, let's see, what's the leading coefficient upstairs? Negative 2. The leading coefficient downstairs, understood 1, negative 2 over 1. So I have a horizontal asymptote at y equal negative 2. Notice I haven't found my y-intercept yet. I can do that in a moment with your help, but I don't think I'm going to need it in this case because of the end behavior. To clarify, I need it because the question asks me to include it. I don't need it in order to graph. So the values I'm interested in are x equal negative 1/2, 3, and negative 1. So I want to make sure those are really identified. So here's negative 1, negative 1/2, 1, 2, 3. So there's the values I'm interested in. The zeros occur at negative 1/2. That's an actual point. And x equal 3. And I have a vertical asymptote at x equal negative 1. Remember those vertical asymptotes are a dashed line that my graph will approach. Next, I have end behavior is at y equal negative 2. Since my end behavior is y equal negative 2, I'm going to find the line y equal negative 2. So it's my graph, my scale. So maybe negative 2 is here. So I'll tell my reader what that value is, and then I'll dash that line. That should be a horizontal line, right? So what does that mean? That when x gets very large, what does very large mean in this case? Anything bigger than 3, my graph will approach this asymptote, maybe from below, maybe from above, but either way, those y values will have to be negative. Likewise, when x is very small, less than negative 1, I know I'm going to approach this asymptote. In this case, I can graph from the left or the right. I'm standing over here on the left, so I'll graph from the left. So the first place I'm going to put my pencil is next to this asymptote because I know when x gets very small, I approach this asymptote. Now I'm going to work my way back to the right. The first thing I encounter is a vertical asymptote. Remember, this is y equal negative 1. Oh, no, it's not. Yeah, it is. So negative 1 is the value. So I have two choices. My graph can approach the asymptote going upwards or approach the asymptote going downwards. Can't cross the vertical asymptote. Will you tell me, if I'm going this way, can I go up? And what you discover is that you cannot, because to do that I would have to cross the x-axis, and I don't have any zeros in here, so it must go down. So that also tells me where I'm going to draw it. I'm choosing to draw it on the bottom of this asymptote. We mentioned last time that a function can cross its horizontal asymptote. So if you wanted to get creative and cross over this asymptote and then approach from above, that's actually okay. We don't know for sure it doesn't do that. What it doesn't do is intersect the x-axis up here, okay? All right, so here I am. Y equal negative 1 was this vertical asymptote. Immediately to the left, my y value is negative. What I'm going to try to figure out now is, does the y value change signs, or does it keep the same sign? That's indicated from the multiplicity. X equal negative 1 is my asymptote. The multiplicity is 2. That's an even number. If the multiplicity is even, remember, we keep the same sign. If this were a 0, it would look like it bounces. In this case, it's going to be negative on the left and also negative on the right side. So it's going to approach the asymptote the same direction from both sides. The next thing I see is just 0 all the way up here. I wish I had drawn this from higher, so I have to come up here and intersect with this 0. Notice again, I'll be crossing the horizontal asymptote, and that is totally fine. I have to intersect at negative 1/2. The multiplicity is 1, so I'm going to cross over the x-axis to do that. and I'm coming back to x equal 3. At x equal 3, my multiplicity is 1. Again, that's an odd number. So I need to cross the x-axis, and then I can approach my end behavior. So this looks like the graph. 10-point quiz, I just got 9 out of 10. How do I get that last point? Remember, the directions ask me also to find the y-intercept. What I'm going to do is use some confirmation techniques. Based on my graph, the y-intercept better be a positive y-coordinate. So I'm just going to look and see. Remember, I can plug 0 in for x in the factored form, but here's a case where we have it in expanded form. If x is 0, all this goes to 0. I'm left with 3 over 1. 3 divided by 1 is 1. So the y-intercept, remember that was the question I need to answer, is 0, 3, and I can indicate that over here by just telling my reader that we hit here at y equals 3 is the y-coordinate of the y-intercept. So this is the graph of problem number 6 on those exercises. We're going to come right back and look at problem number 3 as the final example. G of x equals x minus 1 squared over x plus 2. Now with a little bit of practice, I think we know what we're doing. The zeros occur when the numerator is 0. The only value that makes the top 0 is x equal 1, because that factor is being squared, its multiplicity is 2. The vertical asymptote occurs when the denominator is 0, x plus 2, so the vertical asymptote is at x equal negative 2, and that multiplicity is 1. The end behavior, in our last 2 examples, we had a horizontal asymptote. That horizontal asymptote was at the x-axis y equals 0 when the degree of the numerator was larger than the degree of the numerator. In the second example, we had a horizontal asymptote at y equal negative 2. That was the quotient of the leading coefficients because the degree of the numerator was equal to the degree of the denominator. So we look at the degrees here. The degree upstairs, remember, if we expanded this, we don't have to do this, but we would get x squared minus 2x plus 1 over x plus 2. So the degree upstairs is 2, the degree downstairs is 1. So here's the case where the degree of the numerator is bigger than the degree of the denominator. In that instance, you have no horizontal asymptote. So I don't have a horizontal asymptote. But that doesn't mean I don't have end behavior. So this is the one that's most confusing when you work, because you often say, well, there's no horizontal asymptote, so you're done. We still want to know what the end behavior is. It's actually not tricky at all to discover. So this goes to the question about how do you find an oblique asymptote, which I will comment on in a second, but first I'm going to tell you all we need to know. I'm going to get rid of everything except the leading terms. I would get x squared over x. Reduce that fraction. What is x squared over x? It looks like y equals x. Take out your finger and draw the line y equals x, and it will look like this. So what does that mean? That the right-hand side is going up and the left-hand side is going down. Think about polynomials. That's the end behavior for our function as well. So now I know my end behavior is up on the right and down on the left, and I'm totally fine with you identifying your end behavior with 2 arrows. We talked about that in the session. So that's it. I know the end behavior. I know the zeros. I know the vertical asymptotes. I know the end behavior. I'm ready to graph this thing. We can also find the y-intercept, right? I'll find mine at the end. Again, that's just something to confirm my graph. And then we'll talk about oblique asymptotes. So let's see if we can graph this thing. The x values I'm most interested in are x equal 1 and x equal negative 2. So we let negative 2 fall over here. Remember, that's going to be a vertical asymptote. So here's negative 2. And at x equal 1, we have a 0. So that's an actual point on my graph. So then how do we graph this? Well, we know the end behavior. That's how. So when x is large, what does large mean? Bigger than 1. What does small mean? Less than negative 2. So when x is bigger than 1, my graph has to be going up. So I just draw a graph that's going up. So it's going up here. And then I come and I intersect at x equal 1, and I have choices. I can cross over if my y value changes signs, or I can bounce and come back up if my y value keeps the same sign. Let's see. X equal 1 is 0. The multiplicity is 2. That's even. So I'm going to keep the same y values in my graph. I encounter a vertical asymptote. What are my choices? Up or down? I can't go down because I have no zeros here, so I've got to keep going up. Immediately to the right of this asymptote, my y value is positive. Immediately to the left, I will either keep the same y value or I will change y values. The vertical asymptote was at x equal negative 2. Its multiplicity was 1. That's an odd number. So if I'm positive on the right, I must be negative on the left. And then what? Well, remember we had 3 options for end behavior. I could level off somewhere. I would know if I leveled off if I saw a horizontal asymptote. I don't. So maybe I could, so my other choices would go up or go down. This thing could go up, why not? Because it would have to cross the x-axis and we would have a 0 in there, but we don't have a 0, that's just a flake on my board, okay? So there's no 0 to cross, so we just ruled out it can't go up and it can't level off, so what must it do? Go down, which is exactly what we stated was the end behavior a while ago. And this is the graph, not bad. Oh, you want the y-intercept? Remember to find the y-intercept, I replaced x with 0, so the y-intercept for this time. Replace x with 0, we can do that in either of these guys. We get y equal 1/2, so the y-intercept is 0, 1/2. How do I indicate that on my graph? So here's our graph. This is pretty good. Now, wait a minute, I need the oblique asymptote. If I go back up here where I found the end behavior, I did that by getting rid of all the extra stuff at the ends and just said, look at the quotient of leading terms. To find the oblique asymptote, I actually need to take that ratio. That is, I need to take this guy and divide by this guy, okay? You can do that with synthetic substitute, synthetic division, or long division. If we use synthetic division, we would take just the coefficients here. I'll do this in different colors. So 1, -2, and 1. Remember, if I'm using synthetic division, I'm looking for the value that makes this guy 0, dividing by x plus 2. So -2 goes here. First guy comes straight down 1. Multiply and add. -2 times 1 is -2. Add 2 is -4. I don't even care what comes next, but we'll see. -2 times -4 is +8 plus 1 is 9. So what does that mean? That if I took this ratio, I would get x minus 4, remainder 9. That x minus 4, that's your oblique asymptote. Notice if we drew the graph of y equal x minus 4, it would be right in through here somewhere. So this graph would eventually get close to the function here and down there. So our graph is pretty good even without having found the oblique asymptote. But now we found it, x minus 4. So it would be more accurate. I would need to draw this to scale and move this whole thing down. But I'm pretty happy with that graph. And now you've seen an oblique asymptote. Can you see that? The oblique asymptote was three examples with 3 different end behaviors. I hope that was helpful. So shoot me an email if you have any questions. See you guys next time.